Today under statistical thermodynamics, we will be looking at the electronic partition function. Now the electronic partition function is given as Q is equal to summation GE e raised to minus EE by KT, where GE is the electronic statistical weight factor and EE is the electronic energy. Now this electronic energy, it could be obtained from the solution of Schrodinger wave equation, but more conveniently the energy, that is the electronic energy, could be obtained from the spectroscopic data. That is, we could write EE is equal to h mu, and that is h3 into omega, where omega could be obtained from the spectroscopic studies. That is the difference between the two spectroscopic lines could be obtained. Omega, h is Planck's constant and c is the velocity of light. For most of the molecules, the excited energy level, it lies very far away as compared to KT, and hence we are considering that all the molecules, they are present in the ground state, and the contribution of the electronic partition function of the excited state, or the only very few particles are present in the excited state, and the contribution arising from this very few particle, it may be neglected, and as a result when we expand this, we will get Q is equal to E, and generally for ground state the energy is 0, so we are substituting 0, so this whole will be 0 and e raised to 0 will be 1, and all the higher terms, as they are very less than 1, these higher terms could be neglected, and as a result we get the electronic partition function is equal to G0. That is, the electronic partition function is simply equal to the degeneracy of the ground state, and the degeneracy of the ground state, it could be obtained from Russell-Saunders coupling, and according to Russell-Saunders coupling, the degeneracy, it is obtained as 2j plus 1, where j is the angular momentum quantum number, and this 2j plus 1 from the term symbol, generally we know that term symbol L, we write it as 2s plus 1 j, and j is equal to L plus s. So from the information of L and S, we could get j, and when we substitute j over here, we could get the electronic partition function. Okay, so hence we could get the electronic partition function, and we have seen the 4 types of partition function. That is, translation partition function, it is given by 2 pi mkt raised to 3 by 2 v by h cube. Rotational partition function 8 pi square I kt upon sigma h square. Vibrational partition function is given by this expression, and the electronic partition function will be given by this expression. Magnitude of this partition functions are as follows. For translation partition function, it is between 10 raised to 28 to 10 raised to 32, means this much amount of states are accessible for any particular particle. Similarly, for rotation, it is between 10 to 1000. For vibrational, it is between 1 to 10, and for electronic, it depends on system to system. Generally, it is between 1 to 10. So this many states are available for different types of partition function for a particular system. Further, if we are considering a monoatomic molecule, in monoatomic molecule only translational and electronic partition function will exist. So the total partition function for monoatomic molecule will be translation into electronic. For diatomic molecule, all the 4 partition functions will exist, because rotational and vibrational will be shown only by the diatomic molecule. So all the 4 for diatomic molecule, the total will be the multiplication of all the 4 partition function. Thank you very much.